This is the final, fourth part of lecture 1 of linear algebra. And this part is about complex numbers and some other numbers. This part is not very important for this lecture, but we will use complex numbers in one construction described in this part in the future. So because of this, I decided to include it into the first lecture. Okay, complex numbers, what are they? Probably you already met complex numbers in the high school. If you didn't, it's absolutely fine. I'm going to describe them now. We can obtain complex numbers by adjoining an element usually denoted by I to real numbers, such that square of this element equals -1. I square is -1. Then you can form a set that consists of all possible sums, a plus bi, where a and b are any real numbers. You define this set to be a set of complex numbers, denoted by C, like this, bold C. And then you equip this set with addition and multiplication operations, such that all usual rules of addition multiplication holds. Namely, you define addition of two complex numbers using this formula. A plus bi plus c plus di is just a plus c plus b plus d times I. You just group common terms together. Similarly, if you want to multiply two complex numbers, a plus bi times c plus di, first what you have to do, you just get rid of brackets. You just simplify this expression, expand. You get something like this. Then you keep in mind that I square is -1. So you get rid of I square here and put here -1. And then you group common terms together. And then you have this number, AC minus BD plus AD plus BC times I. Note that AC minus BD is a real number, AD plus BC is a real number. So this is a complex number by our definition. This gives you the way how to add complex numbers and how to multiply them. You can multiply complex numbers by -1 and add to another complex number. This gives you the way how to subtract complex numbers. And finally, with some additional efforts, which we're not going to do now, you can actually divide complex numbers. If you need more details, you can look at the lecture notes or in the book or just on Wikipedia. This is quite well known. The most important basically slogan that you can work with complex numbers as with real numbers. In particular, almost everything we describe in this lecture can be generalized for complex numbers. For example, we can consider vectors whose entries are complex numbers. We can consider matrices whose entries are complex numbers. You can multiply them. Everything is going to be almost the same. There's still some differences. So for example, dot product cannot be immediately generalized for complex vectors. You have to adjust it a little bit, which we will do in the very end of this semester. But most of the results you can obtain in linear algebra, you can do for vectors and for matrices with complex entries. So, but this is not why complex numbers are so important. There are two reasons why they're so important. One reason is that it's very often that some problems about real numbers can be solved using complex numbers. We will see some examples in the future. And another reason, more theoretical, then complex numbers satisfy very beautiful property described on the next slide. For complex numbers, we have very important result called fundamental theorem of algebra. Some people consider this as one of the biggest results in algebra. And this is indeed probably the most useful result in algebra. It basically tells you the following. So if you take any polynomial with complex coefficients and a positive degree, then it has a root among complex numbers. It basically, if you want to solve polynomial equation f equals 0, you can always find the complex numbers that satisfy this equation. This is not true for real numbers. For example, polynomial x squared plus 1 doesn't have any root in real numbers. X squared plus 1 doesn't have real solutions, but of course it has complex solution. This is the number I. Okay, So this number lambda in the theorem, it's usually said to be a root of the polynomial. Yeah. Okay, so this is very important property. We basically can use this property to derive the following corollary with some additional technique. So this corollary says that if you have any polynomial with complex coefficient, this polynomial can be factorized as a product of polynomial of degree 1. Of course, here polynomial should be of positive degree. Yeah. So note that this corollary implies theorem on this slide. This corollary implies fundamental theorem of algebra, because if you take a polynomial f and you factorize it like this, that of course it has a root. It has lambda 1, lambda 2, lambda n. It actually tells you more. It has n roots. They may be repeated roots, of course. Yeah. And vice versa, as I already said, the theorem in the center of the slide implies corollary if you know how to divide polynomial by another polynomial with a remainder. We're not going to cover it now, but you can take a look on the lecture notes or in the book for more details to see what's going on. Okay, this result will be used a few times in this course, and we cannot prove this. It's outside of the scope of this course. It's quite complicated and involved, but it's very important, I think, to check at least this theorem in some small cases. So, for example, you can check how to apply the theorem to polynomials of degree 2. In particular, we know that every quadratic polynomial with complex coefficients can be factorized as a product of polynomials of degree 1. If you can do this in examples, this is a good illustration for the theorem. We will have some tutorial problems about this. Okay, so as I already mentioned, a lot of things in this course can be generalized for complex numbers. Moreover, some results in this course for real numbers can be proved using complex numbers. Are there any other numbers which we're going to use? Occasionally, yes. Occasionally, we're going to use some other numbers. But before describing them, let me basically just ask a question. What do we mean by numbers? Mathematicians reserve a special name for some numbers which can be used in linear algebra. This name is called a field. What is a field? First of all, it's a set. Usually, people denote fields by F letter, like this. Bold F stands for field. So F is some set. You take some set, and this set is called a field if you can equip it with two operations, addition and multiplication. And this operation is basically part of the field, such that your set behaves as usual numbers when it's equipped with this operation. What do I mean by usual numbers? It basically means that usual properties of real or complex numbers satisfy for this set and for this addition operation. I listed these properties here. It looks a bit abstract, but you can take it informally as much as possible. So if you read each properties among these 8 properties, it's quite natural. So first of all, this set must contain some element, usually denoted by 0, which actually behaves like 0. So like 0 plus x is x for every x in F. So it's like natural. Similarly, this element, the set must have an element which behaves like 1. What does it mean? It means if you multiply this element by any other elements, you get another element. So 1 times x equal x. So it's also usually denoted by 1. Yeah. Then addition and multiplication must be commutative. A plus b should be b plus a. Yeah, it's like it's very natural. Then addition and multiplication must be associative. A plus b plus c should be a plus b plus c, no matter how we put brackets there. The same for multiplication. This is properties 4 and 5. We already saw many of these properties for matrices, actually, in this lecture. Then we should have a rule which link together addition and multiplication. This is rule number 6. A times b plus c, it's a times b plus a times c. Sometimes it's called distributive law, distributive property. We already met this also when we multiply and add matrices. And finally, the most probably important two properties, we have to be able to subtract elements, and we have to be able to divide elements of the field. Namely, for two elements A and B in the field, there should be some element, which I denoted by blue star, such that A equal blue star plus B. So basically, this blue star is just A minus B. And if A is 0, then 0 minus B shortcutted traditionally as minus B. This is absolutely the same what we have for real numbers. Similarly, for every two elements A and B, if B is not 0, it should exist an element that behaves like A over B. To be precise, it should be an element which I denoted on the slide green star, such that green star times B is A. So this A can be denoted by A over B. Again, A over B is some element in F, such that if you multiply it by B, you get A. So if A is 1, then this element traditionally denoted like 1 over B or B to the power of minus 1. Sometimes it's called multiplicative inverse of B. Okay, so this is quite common, and a lot of things we're going to do in linear algebra can be generalized for any field. And this is actually very useful. A lot of results becomes true in much more general settings. But there's special fields which plays very important role in cryptography and in computer science because they finite. Basically, they are called finite fields. What are finite fields? These are fields which consist of finitely many elements. So the natural question, how to construct such fields? Do they exist? Of course they exist. And there's a very standard recipe how to construct a lot of finite fields which consist of prime number of elements. Basically, this is the only thing you have to know about fields from this part of this lecture, because we're going to use this construction several times in some examples. And this is quite important for cryptography. This is quite important for computer science. Okay, let's Fp be the finite set consisting of p integers, 0, 1, 2, up to p minus 1. P is excluded. Then we want to equip this set with addition multiplication. Okay, one naive way, you can just take two integers from this set and you just add them and multiply. But this rule not going to work because you can accidentally get a number that is not in the set. Then you have to adjust it. You have to take the remainder of this number when you divide by p. This gives you these two rules, how to add elements from the set and how to multiply. A plus b is the remainder of the integer a plus b when divided by p. And likewise, a times b and the remainder of the integer a times b when divided by p. In the accelerated proofs and problem solving course, this set is probably going to be denoted by ZP. This is another notation for this set. I would prefer to call it FP because F stands for the field. And in accelerated proofs and problem solving course, you're going to prove that this set equipped with these two operations is actually a field. We're not going to prove it, take it for granted, or you can Google the proof, or you can look at the lecture notes of accelerated algebra, accelerated proofs and problem solving course. Okay, here's an example. You take P to be 1973. It's a prime, you can check it. Then, for example, if you want to divide any element A in this set Fp by 45, then this is the same as just to multiply this element by 570. Why? Because if you multiply 45 by 570, you get some huge integer. But if you take its remainder when you divide by 1973, you get 1. So by our definition, 45 times 570 is 1. So A divided by 45 is the same as A times 570. This is how it works. For all examples, our prime P going to be small. 2, 3, 4, 5, 7. Okay, I made small mistake. I said 4, but 4 is not a prime. Okay, this is a nice question. This construction gives us example of a field that consists of 2 elements. It also gives us example of a field that consists of 3 elements. This is just 0, 1, 2. It also gives us example of a field that consists of 5 elements. and field of consists of 7 elements. What about 4? Unfortunately, this construction is not applicable when you substitute P to be 4, because 4 is not a prime. For if you just put here in this slide P to be 4, it's not going to work. It's not going to be a field. Basically, because 2 times 2 is 4, it should be 0. 4, yeah, so you get 2 times 2 is 0, it's a problem. It basically means that 2 doesn't have an inverse, multiplicative inverse in this field. So there should be another way how to construct the field of 4 elements, if such way exists. Such way actually exists. It's a little bit abstract. So basically, if you don't want to listen to the remaining part of this lecture, just skip it. We're not going to use field of 4 elements, and we're not going to use any other finite fields rather than this FP described here. But I think if you're curious how to define field of 4 elements, I think it's fun, and I decided to include it. Okay, you start with a field F2 consisting of 2 elements, 0 and 1. It's very easy to add and multiply numbers in this field. 0 plus 1 is 1, 0 plus 0 is 0, 0 times 1 is 0, 1 times 1 is 1, 1 plus 1 is 0. So everything is very explicit in this field, consists of only 2 elements. This field plays a crucial role in computer science. Okay, then you do the same trick as we did with complex numbers. You add to this field a new element, which I denoted by T by some reason, such that this element satisfies this equation. T squared is T plus 1. This is a rule. This is why I put it into the black box. It's just a rule. Okay, then you consider all possible sums that looks like A plus BT, where A and B are in F2. But look, for A, there's 2 possibilities, 0 and 1. For B, there's 2 possibilities, 0 and 1. So we actually have just 4 elements. Which elements we have? 0 plus 0 times T, which is we can denote by 0. 0 plus 1 times T, which we can denote by T. Then 1 plus 0 times T, which we can just denote by 1. And then we have 1 plus 1 times T, which we can just denote by 1 plus T. That's it. This is all 4 elements in this set. We can denote this set by F4. And now the only question, how to equip it with addition multiplication, such that all our properties described a few slides ago satisfied. But we can do it absolutely like we did for complex numbers. Namely, addition is very natural. I don't even want to explain it. But multiplication, a little bit more complicated, but roughly the same. You start with 2 numbers in F4, A plus BT and C plus DT. You multiply it. You get rid of brackets. You get this long expression. You expand this. And then you notice that by our rule, T squared is T plus 1. So you substitute T plus 1 here. And then you group common terms together. And then you have AC plus BD plus AD plus BC plus BD times T. This gives you the rule how to multiply elements in F4. Okay, one can check, this is actually a nice exercise, that these 2 rules define you a field F4. Okay, you have 4 elements, 0, 1, T, 1 plus T, and you have the rules how to multiply them and add. This is field of 4 elements. Okay, if you need a little bit more fun, you can basically repeat this construction to get a lot of fields with P square elements. Let me give you just one example, and we finish this lecture. You take P prime to be 2063. It's a prime. You can check it's a prime. Then you can observe that there's no element in FP in this field of consisting of P elements such that A squared is minus 1. Basically, if you want to solve equation, A squared is equals to minus 1 in FP. There's no solution. How to check it? The simplest way, you run a simple computer program and you check there's no, every element in FP, if you take it square, you never get minus 1. In this case, minus 1, of course, is 2062. Okay, of course, there's a deeper reason why this is happening. And this reason we cannot explain it now, but you will learn it in Introduction to Number Theory course in the year 3, if you're going to take it. It's not compulsory course. And the reason is that if you divide 2063 by 4 with the remainder is 3. And this one result in number theory tells you if you have prime like this, then equation a squared equals -1 in this field doesn't have solution. There's no element in this field whose square is -1. Okay, in particular, this implies that this polynomial x squared plus 1 doesn't have a root in FP. So this means that it's irreducible. Irreducible means you cannot factorize it as a product of polynomials of smaller degree. So if it had a root, it would be a product x minus lambda 1 times x minus lambda 2, where lambda 1 and lambda 2 are roots. But we already know it doesn't have any roots, so it cannot be factorized. So it's irreducible. And then you repeat line by line our construction for complex numbers, but replacing real numbers with FP. You introduce element t such that t squared is -1. And then you consider all possible sums a plus bt, where a and b are elements of the field FP. And then you denote this new set consisted of all these sums by fq, where q is p squared. And then you equip this set with addition multiplication, which is copy-pasted from the complex number slide. That's it. It's absolutely the same as for complex numbers. And then you can check that this is a field consisting of p square elements. Okay. So this construction, for example, can be used to construct a field of 9 elements. Yeah. However, for example, this or similar construction cannot be used to construct a field of 6 elements that consist of 6 elements. And there's a deep reason for this, because there is no field consisting of 6 elements. And you will be able to prove this using linear algebra methods in the end of this semester. Okay, let me stop this lecture.